All right, the next section we're going to talk about is section 4.7, applied optimization. These are all word problems, and the answer to all these questions, or at least how the questions are phrased, the answer to them should be some sort of minimum or maximum amount of something. So, for instance, in this first example, example 1, we're told that we have a piece of metal wire, and it has a length of L, and then we're going to go ahead and bend it into the shape of a rectangle. So when we do that, of course, there's lots of different rectangles that we could create. We could create a perfect square. We could create a rectangle, maybe one that's very long but skinny, or the opposite way. There's a whole collection of rectangles that we can make. Now, we can't create any rectangle that we want because we do not have any amount of length that we want. We have a specific but fixed amount of wire, L. So we want to figure out the area of this rectangle. So we can just say that this is the length L, this is the width of the rectangle W, and then the area is therefore length times width. Now the question becomes, how do we figure out what the maximum area is? Or at least what are the dimensions that have a maximum area? Well, right now, if we take our area equation, it's technically a function of two variables. But this is Calc 1, where we're doing functions of one variable. So something's got to change about this. The other thing we really should think about here is that this actually isn't a function of two variables. It only looks like it is. Because if, for instance, if I tell you how big the length is, let's make this a concrete example. Let's say for our purposes, the amount of wire that we have is, let's say L is equal to 10. And if I tell you that the length is 4, well then, what does the width have to be? Well, for a rectangle, we know that if this is 4, that means this side is 4. So that means in total now we've used 8, I don't know, let's say inches. Okay, let's make this concrete. Let's just say inches. Well, we've already used 8 of the 10 inches, so that means there has to be 1 inch left. So really, we know that based on the fact that the perimeter has to be this amount, the perimeter has to be equal to 10, that tells us that we really only have 1 degree of freedom. We don't have 2 degrees of freedom. If we set a value for L, that doesn't mean that, for the length L, that doesn't mean that the width W can be anything it wants to be. As soon as we pick a value for the length, that automatically determines what the width has to be. So we really only have 1 degree of freedom. So there is a way that we can take this equation that involves 2 variables and write it so that it only depends on one of the 2 variables. And the way that we're going to do this is effectively perimeter. Because that's exactly how we figured out that we had 1 inch to use here and here. Is we said, okay, we have our total length minus 2 copies of the length we used, 4 in this case, and then that has to be split between the 2 sides. So what we'll do to make this a little bit more concrete, or to make it a little bit more applicable to the problem we have in hand, we'll come up with an expression for the perimeter, L, which is 2L plus 2W must equal capital L, the amount, the length of wire. So then we can take this equation, capital L equals, and solve it for one of the 2 variables. It doesn't matter which one. Let's just choose L. So then we'll have capital L minus 2W all over 2. Has to be equal to the length. Then we can use this and substitute it into our area equation, which will then create for us a function of one variable alone. So pretty much in all these optimization problems, you'll have some sort of equation, and that equation may very well have more than one variable in it, but there's always going to be some sort of limited quantity. Maybe it's a finite amount of paint that you're using. Maybe it's a finite amount of wire you're using. Or maybe the distance from here to here is a maximum of this. There's always going to be some sort of quantity that's limited. We call that the constraint. And you can always use your constraint to take your function, your objective function, the thing you're trying to minimize or maximize, and you can reduce the dimensionality of it down from maybe a function of two variables seemingly down to a function of one variable. So you should always be able to bring things down to one variable in this class, at least for these problems. Okay, so now that we have that, we want to think about on what sort of interval is it defined. Well, if we go ahead and think about it, this interval here is going to tell us what is the smallest and largest value of the variable. Since our variable is w, we have to think what mathematically and physically is the smallest that this w can be. Well, since we're constructing a literal rectangle, we know that the width can't be a negative number. So the smallest the width could conceivably be is 0. Now, of course, some of you may argue, well, if you have a rectangle where the one side length is 0, is it really a rectangle at all? That's a great question. But what we're going to think about here is, let's think about, we can say, sure, as we make the width smaller and smaller and smaller, we get this family of rectangles. Right? We start with a large width, and if we progressively make it smaller and smaller and smaller, what is that natural conclusion? If you push it to the limit, what is that value? In this case, 0. So whether or not you want to actually consider something with a 0 width as a rectangle or not, you can leave that to philosophy. But for us, we're going to say that's the furthest we can push it conceptually. So that's going to be 0. Well, what's the biggest w can be? That might be a little bit trickier. Usually one of your two endpoints, usually one of the two is easy to get, the other one's a little bit harder. Well, could it be, for instance, let's think, could the width be L? Is that the biggest it could be? No, it couldn't be, because remember, for the perimeter, if we make this, whatever length this is, we also have to use that same amount of material on this side. So it can't be L, because if we use all the material here, then we can't even build anything here. What about L over 2 then? If we use half the length here, half the length here, then there's no material left for these ends. But at that point, that's sort of like the opposite thing, where our rectangle is all width and no length, in which case we get something like this. They kind of squeeze together this way. So L over 2 will be that upper endpoint. Another way you can get these values is by looking at the function. We know that the area of our rectangle has to be, it can't be negative. And if you see that if we made w any bigger than L over 2, this amount in the parentheses here, we would be subtracting something bigger than L from L, which would make this in parentheses negative, which would make the area negative, which would be nonsensical. So the furthest that we can push the value of this right endpoint before it makes the area negative, that's going to be the upper bound. So no matter how you think about it. So now that we have our interval, we're now going to go ahead and find critical points. So we take a derivative, and this would be derivative of the first times the second left alone plus the first times the derivative of the second, which is 1. This entire thing should clean up pretty nicely into L over 2 minus 2w. If you collect like terms and do all that stuff, you should get something like that. So now, this is a polynomial, so we know that this is continuous everywhere. So that means we don't have to check and see where the derivative does not exist. We're not going to find any critical points that way because this always exists. So instead, we only need to check and see where this equals 0. And if you solve this, we get that the width is going to be L over 4. So now that we have the width of L over 4, we're going to compare the value at the endpoints. So the left endpoint is 0, the right endpoint is L over 2, and then our single critical value we found. If we plug in these two values, 0 and L over 2, we'll find that we get 0 area. And if we plug in L over 4, you'll find that we get L squared over 16. So clearly, this is the maximum. So we know the maximum area that we can receive is going to be L squared over 16. And here's where it's really tempting for some of these optimization problems. As soon as you find the maximum, there's this sort of inclination to say that you're done. You're finished with the problem and you want to move on. But make sure you go back to the actual optimization problem and read it again. Because sometimes they ask you for something specific. In this case, they ask us, what are the dimensions of the rectangle which maximize the area? So they don't actually want to know this value at all. They don't care about this value. They just want to know what is the length and what is the width that make this rectangle have maximum area. So we know what the width is. We found that earlier. So what we want to do now is get the length. Well, we can get the length from using the relationship right here, the perimeter relationship. Go ahead and plug in our value of L. When you do that, you'll find that a length of L over 4 also is what we get. So this means, together, that the rectangle of maximum area is a square, actually. So its dimensions are L over 4 by L over 4. That's the actual answer.